To get the most out of this video, you should already know how to recognize and write expressions for the three trig ratios, be familiar with the trig ratio buttons on your calculator, and know how to apply these skills to calculate unknown sides and angles in a right-angled triangle. If not, I recommend that you watch the first relevant videos in this series before continuing here. It is also preferable that you are familiar with angles measured in degrees and minutes and how to use the degrees, minutes, seconds button on your calculator. But this will only be included in one example. In this video, we will apply all these skills in examples involving angles of elevation and depression. So what are angles of elevation and depression? If you imagine a line from your eye to an object you're observing, it's known as your line of sight. If you look straight ahead without tilting your head, then this line is parallel to the flat ground and is known as a horizontal line of sight. When you tilt your head to look up at an object, the angle turned from the horizontal line of sight to the new line of sight is known as the angle of elevation. And when you look down to an object, the angle is known as the angle of depression. More formally, we can define an angle of elevation as the angle between the horizontal and the line of sight when looking above the horizontal. And the angle of depression is the angle between the horizontal and the line of sight when looking below the horizontal. Imagine standing on top of a building, looking downward at a friend on the ground. At the same time, your friend looks up to see you. At that moment, the angles of elevation and depression are equal. Of course, common sense tells us that the angles should be the same. Your friend will need to look up by the same amount that you need to look down. Assume you are looking each other directly in the eye. You may recall special angles formed when a line cuts two parallel lines. Well, we have a pair of alternate angles in the parallel lines formed by the two imaginary horizontal lines of sight. Alternate angles in parallel lines are always equal. This can be useful when solving problems involving angles of elevation or depression, giving you a choice of two right triangles to work with. Now let's solve some basic trigonometry problems involving angles of elevation and depression. In this first example, a diagram is provided, but we need to match the information. This problem is almost identical to a problem solved in an earlier video, the only difference being that the term angle of elevation wasn't previously used, and you're expected to transcribe the information onto your diagram as well. We are told that at a point 20 meters from the base of a tree, so we can mark this distance as 20 meters, the angle of elevation from the ground to the top of the tree is 17 degrees. So we mark this angle as 17 degrees. We can assume the tree is vertical and the ground is horizontal and flat, and so we have a right angle here. We are asked to determine the height of the tree. We can label it h, or any variable you choose. The problem can be simplified and represented by this right-angled triangle. Labeling our sides and using SOHCAHTOA, we see that the tan ratio is required. Opposite over adjacent is tan, so h over 20 equals tan of 17 degrees. Multiplying both sides by 20, we find that h must equal 20 multiplied by tan of 17 degrees. Typing this into your calculator gives this result, which equals 6.1 when rounded to one decimal place. Remember to check your calculator is set to degrees here, or you will get the wrong answer. We have found that the height of the tree is approximately 6.1 meters. Pause the video if you'd like to try this second example on your own first. The angle of depression when looking along an anchor pulled tight is 62.1 degrees. The total length of the anchor and chain is 14.3 meters, excluding the part of the anchor buried into the seabed. Find the depth of the water, ignoring the height of the anchor chain above the sea. We can see a right-angled triangle to use, or alternatively, we could use this one. Labelling our sides, we find that the sine ratio is required. Opposite over hypotenuse equals sine. We can transcribe our information and we get d over 14.3 equals sine of 62.1 degrees. Thus, d equals 14.3 multiplied by sine of 62.1, giving us a depth of 12.6 metres, ignoring this exposed part of the anchor chain since the problem told us to do so. If we weren't asked to ignore the part of the chain above the water, we could simply subtract the extra height to give us the actual depth of the water. So for example, if the anchor is tethered here at 50 centimetres above the water, the actual depth will be 12.6 metres. Take away half a metre, telling us that the water is actually 12.1 metres deep. In this example, we will take into consideration the height of the observer, or more accurately, the height of the observer's eyes above the ground. Try it first if you'd like to. A person is standing 15.5 metres out from the base of a lighthouse, looking up to the top of the lighthouse, which they have read is 21.7 metres above the ground. The person's eyes are 1.7 metres above the ground. Find the angle of elevation of their line of sight to the top of the lighthouse. Correct the nearest minute. Since a diagram has not been provided, I will demonstrate the process for you. This will be important for those wishing to master trigonometry and study it at higher levels. Others might find that diagrams are usually provided for them. It's important to visualize the situation described. You might need to read it more than once. Once you have a mental picture, then you can start to draw your diagram, constantly referring back to the information provided. As with the previous examples, I will draw my information over the top of the visualization, but really you only need to draw the right-angled triangle that is represented by the information, as you will soon see. The first value we are given is the distance from the base of the lighthouse to the observer, here. We will assume that this is measured from the centre of the base rather than the edge. Otherwise, the radius of the base would really need to be added to the distance to the observer. We will ignore these intricacies at this level, but more accurate calculations would take such detail into consideration. Then we are told the height of the tower, the lighthouse, so we mark that in. Finally, we are told the height of the observer's eyes, which is this distance here. And of course, we need to know just what it is we are asked to calculate. The angle of elevation here, which I have labelled with a Greek theta. Now we can see the right-angled triangle that we can use, but the height of the lighthouse is not the height of the triangle. We need to subtract the height of the observer's eyes, giving us 20.0 for this side of our triangle. Now we are ready to solve the problem. Labelling the sides with respect to the angle theta, we see that the tan ratio is required. Transcribing our information, we see that the opposite side is 20.0 and the adjacent is 15.5. We need to find the angle that has a tan ratio equal to this fraction. To do this, we use the inverse tan button, pressing Shift first to access it. Your screen should look like this. You might prefer to write it as a division, which is usually a little faster. Notice also that we don't need to include the point 0, but we should include it in our written solutions to show the level of accuracy of the data we are using. Pressing equals gives us the required angle. Rounding to one decimal place would give us an angle of 52.2 degrees or 52 degrees to the nearest degree, which would usually be sufficiently accurate in a question like this. However, the question has specifically asked for an answer to the nearest minute. Pressing the degrees, minutes, seconds button again will change our answer into degrees, minutes and seconds. We see that theta is 52 degrees, 13 minutes and 27.54 seconds. We have less than 30 seconds, which is less than half a minute, so we round down, not up. The angle of elevation to the observer's line of sight is 52 degrees 13 minutes to the nearest minute. A timely reminder that we should not round until the final answer. For example, if you had rounded to 52.2 degrees and then converted to degrees and minutes, you would have ended up with an inaccurate answer of 52 degrees and 12 minutes. It is also important to remind you that you must make sure your calculator is set to degrees, or all your calculations will be wrong. I hope you are now ready to solve trigonometry problems involving angles of elevation and depression. Be sure to watch the final videos in this series for harder applications of trigonometry in right-angled triangles.